I'll start by introducing our speakers. We have Will Schroeder and Spiros. How do you say your last name?
Tarlikis, like CH.
Thank you. I didn't want to butcher it. They're from Kitware. They're here to talk to us about their experience in developing parallel computing algorithms and multi-threading. We're really grateful to have them give their time to talk to us, and they are going to answer questions after a couple of short presentations, and so hopefully you can save up your questions to the end. We can ask them, pick their brain about pretty much anything I think is up for grabs or game. So with that, we'll start with Will, who is the former CEO of Kitware, I believe.
Yes, that's right. Yep.
He's been doing development a long time, and Spiros is a newer developer, but he's also been doing a lot of great work at Kitware. So go ahead, Will.
Okay, thanks, Jess. Please interrupt if you can't hear me or something goes amok with my video feed.
Sure.
So we're going to talk today about multi-threaded computing, shared memory, parallel processing in particular. And I will talk for about 15 minutes, and Spiros will talk for about 15 to 20 minutes. And then that will give us time for questions, 20 minutes or so. So hopefully we have lots of time for conversation and follow-up questions. Before I get started, though, I'd like to thank SCI, Scientific Computing Imaging Institute, and University of Utah, and of course the NIH and IGMS. We have a grant between Utah and Kitware, and it's funded some of this work. Also, I'd like to point out that the presentation is meant to be independent of any implementation details of a particular system or implementation model. You can look at two systems, VTK SMB tools, which is part of the visualization toolkit, VTK, or look at VTK-M, which is an accelerator GPU-based system. It's a wonderful piece of software engineering for GPUs. Both systems, there's lots of examples out there, lots of code, so you can look at this and sort of understand in more detail what it is we're trying to tell you about. The good news today is that we are really limiting the number of implementation concepts to just a small number. Really, what I'll be talking about, which is flying edges, the only thing I use is a parallel for loop, which is just a simple for 0 to n with some functor. A functor is like an operator, paren in C++. It's just a small, typically a small function that's called for each piece of data that you want to operate on. And the functor is invoked on each thread across a subrange, and I'll talk about that in a minute. And it does some stuff like initialize data on the thread. It performs executes the operation, and it may reduce or composite the result of each thread's processing to create a final output. I will talk about those two concepts, and then when Spiros takes over, he'll talk about thread local storage, which relates to the functor initialize and reduce methods. He'll talk about atomics, which you need sometimes to prevent data races and to sort of lock or control execution, synchronize execution. And there are other common built-in functions typically in systems like sorts, fills, transforms. We won't be talking about that today, but they're typically out there. So the implementation concepts are parallel for with a functor, thread local storage, and atomics. So very simple to get your head around. I'll talk about marching cubes versus flying edges, and Spiros is going to talk about surface extraction of 3D unstructured meshes. So the parallel for, just to make it a bit more concrete, you basically invoke it with a for with some range 0 to n, and you give it a functor. And what happens is under the hood, that functor is executed many times with sub-ranges of the actual global range. So it may be each thread will get a piece of the action, and it will execute across the sub-range. And at the end of all that, you're done. So very simple concept. So what Spiros and I want to do today is sort of focus on data dependencies. I'm sorry, we want to focus on common design patterns, which feed into writing good algorithms. It's useful to think about threaded computing in terms of design patterns because there's ways of doing things that are non-intuitive often, but if you've seen the pattern once or twice, then it becomes obvious how do you go about solving particular problems. So the design patterns are roughly, look something like this. First, you want to remove data dependencies. And this is really the heart of a good algorithm, is how do you develop a parallel algorithm that has minimal dependencies across execution threads? And that means identifying computational primitives, whether it's points, cells, or some combination of data that you can operate on fairly independently of other data, because other threads will be working on that other data, and they can't operate on the data at the same time. So the whole key of threaded computing obviously is to find ways to isolate the computation and data movement. And the other surprising thing for people that haven't done a lot of threaded computing is, or parallel computing in general, is that multiple passes are typical. In a sequential algorithm, oftentimes you think of step 1, step 2, step 3, and some sort of deterministic order. And you often think of it, you don't think of it in terms of passes typically. But in parallel computing, oftentimes you make multiple passes to sort of set the stage for the data. You do an initial pass to sort of figure out what you're going to produce as output. You might do another output pass to sort of configure some bookkeeping to sort of figure out where the output's going to be written given the input. And then you may actually do an execution pass where you generate output from the input, and you may have a compositing pass or something like that. So it's not uncommon to have 4 or 5, 6 or more passes in some parallel processing algorithms. And I like to think of parallelism in sort of 2 broad categories. Trivial parallelism, which is basically there's a map of n input primitives to m output primitives. The mapping is typically obvious, direct, and often implicitly defined, and typically only a single parallel pass is required. So a very simple example, given a vector, an array of vectors, compute magnitudes from the vector field. So for each input vector, I do some sort of L2 norm or something like that. And that's usually a simple operation. And then I write the output, which is the magnitude. So for each input vector, I have one output scalar, if you will, magnitude. So very simple, trivial. General parallelism is hard because you have to identify what your basic data primitives are. You have to build an explicit mapping of input to output, and you possibly have to perform reduction and compositing. And typically multiple parallel passes are required. And a good example is isocontouring. You know what the input is, but you don't know what the output is. That's a function of the iso contour value. So a mapping is required, and that makes the algorithm non-trivial. So we're going to start with the first case study, which is an algorithm that we all love, which is marching cubes or marching squares in 2D. And basically, I think most of us know this, but for those that may not, basically you start with a scalar field and you produce an approximation to the isosurface defined as f of x equals some constant or iso value. And typically the output varies dramatically as the iso value is varied. And the algorithm, marching cubes algorithm, here's the very crude depiction. I start with some sort of a volume or a grid. I take a cell of the grid. I do some sort of determination of input and output of each vertex that specifies some sort of case which indexes into a case table. From that case table, then I generate segments, little line primitives in this case, and I also generate intersection points. And as a result, the output ISO line is an approximation to the input actual ISO surface. So in this case, the pixel square or the voxel cube is the computational primitive. So you're basically processing voxel by voxel. So just to summarize, the Marching Cube's 3D algorithm for each voxel cell in a volume, you need to access the 8 voxel values. You need to compute the case. And that means basically determining in out of each voxel value, above or below the ISO value. And depending on the case, you'll produce intersection points and triangles. Then you add the points and triangles to the output, and you optionally merge coincident points if you're interested in merging points. So here's some of the problems with marching cubes as is described in the literature. First of all, voxel values are accessed up to 8 times. That's a lot of data, extra data accesses that you don't need to do. Edge intersections are performed up to 4 times. So each edge in a volume, interior edges, can be used by 4 different voxels. So that's potentially reproducing, duplicating computation. Also, because you're on the fly generating points and triangles as output, you need dynamic arrays to insert output points and triangles. And that means you're doing repeated resizing, memory allocation, and so on, which requires blocking threads. So as each thread tries to write to the output, they each have to take their turn, and that becomes a bottleneck. And that's a bad thing. And finally, if you're doing point merging, typically use a spatial or topological hash. Again, you've got some blocking going on. Again, a very bad thing. So how do we get around these bottlenecks and performance issues? A few years ago, we came up with an algorithm we call flying edges. It's shared memory, multi-threaded algorithm. And it's basically a 4-pass algorithm. It only uses the parallel for loop concept. And the computational primitive is volume edges, not cubes like marching cubes. It's volume edges. And some of the features of it is it visits voxel values only once, only one time. It performs edge intersections only once. It performs one-time exact memory allocation, so there's no realloc. And the point merging bottleneck is eliminated. So it eliminates a lot of the problems with marching cubes. So how does it work? Well, this diagram sort of gives you a rough idea. I'm guessing there'll be questions later, but let me give it a shot. So we have our volume, which is that gray box in the center. And in the volume, we have X volume edges or volume X edges. And those volume X edges consist of little voxel edges, X edges. And each voxel has associated with it what's called a voxel triad. That's an X, Y, Z axis corresponding to the voxel value. And that controls basically the intersection of ISO value on each of the sub edges of the voxel. And I'll show you later, you take multiple of those voxel triads, combine them together, and that gives you the complete state of the voxel. On the left-hand side of the gray box, you'll see there's a plane which corresponds to edge metadata. This is a bookkeeping construct that keeps track of all the intersection points or the points that will be generated during ISO contouring and the number of triangles for each edge, X edge, volume X edge. And it also has something called trim edges, which just is a limit on the positive and negative side of the edge where data resides. data that may affect the output. So in order to actually run the algorithm, all we determine is edge cases, X edge cases, shown in the right of the gray box. And we have 4 edge cases. We have 1, 2, 3, 4, depending on which of the endpoints values of the endpoints of the edge take. If there's something below and above the ISO value, we have case 1. If there's something the opposite, above and below, we have a case 2, and then we may have case 3 and 0, which produce no intersections because the ISO value does not pass through the edges. And so what we do is we take these edge cases, we compute them in parallel across all volume X edges simultaneously. There's no dependency across the edge computation. Once we've done that, we combine these edge cases. That produces basically a volume marching cubes case. And that marching cubes case is then used in the standard way to produce triangles and intersections. So let me jump ahead. So I'm going to go through the 4 passes and hopefully give you a bit more information that'll help to make this comprehensible. So the way pass 1 works, for each volume X edge, we simply classify the voxel value above or below an ISO value to determine the voxel. In this case, it's the voxel edge case. In order to do that, we count the number of voxel edge intersections, edge case 1 or edge case 2. Otherwise, there's 0 voxel edge X edge intersections. We also keep track of edge trim. That's the left-hand and right-hand side of the edge where data may be, output data may be produced. This is just useful for eliminating or reducing computation. We also update the edge metadata that I showed you in the previous slide. And note that as we do this carefully, we only access each volume voxel value once. So we're not accessing it 8 times, we're only accessing it 1 time. The second pass, again, we process volume X edges, except we're not processing the actual data, we're processing metadata. And the metadata is a compact form of basically indicating what kind of data lies on each volume X edge. And also we use the trim edges so we can skip over much of the volume. If a trim edge says that there's nothing along the edge, we can skip it. If trim edges say there's nothing on a slice, we can skip the entire slice. We then combine 4 edges, which form a voxel cube to determine the marching cubes case. We use a modified marching cubes case table to determine the number of XY intersections. In the previous pass, we computed the number of X intersections, and we also keep track of the number of triangles generated. And then we update that edge's metadata. Once we've processed all the volume X edges, we then compute the output shape. So we perform a prefix sum, which is basically just a summation over the metadata, and to determine the total number of output primitives, points, and triangles. It also helps define the numbering for each point and triangle generated. So on each edge metadata after the prefix sum will indicate the starting point ID and the starting triangle ID to be generated along the output of that edge. And a funny note is that prefix sums often can be performed in parallel, but oftentimes it's not much faster than running sequentially, depending on the hardware and underlying software system. And once the output shape is computed, prefix sum is computed, we basically can do a one-time exact memory allocation. So no reallocs. Now in pass 4, we start with each volume X edge again. Again, we're processing, we're processing the volume X edges only when necessary, only those X edges that the trim indicates that there's some data residing in. So we initialize a output iterator with a starting point ID and triangle ID. This is for each edge, remember. We combine the voxel X edge cases to compute the marching cubes case. We produce output points and triangles for each voxel triad. We move to the next voxel triad. That's an iterative move to the next voxel along the volume X edge, updating the point and triangle IDs. And when we do it like this with these sort of run along the row iterators, we basically do not have to do any point merging because we know from the prefix sum where the point IDs for that edge and the triangle IDs for that edge, we know the starting values for those. So we can just run along the edge and just generate things and write the output directly to the allocated arrays. And also note, because we're using this this voxel triad, we only compute edge intersection one time. So that saves a lot of work. So this is a typical example. I mean, every parallel algorithm is different. On the left, you see some sequential speed ups. Flying edges is about 5.22 times faster than sort of a basic marching cubes algorithm. An optimized marching cubes algorithm where you can parallel process and has a better point merging algorithm is a little faster than the basic marching cubes algorithm. And synchronized templates, which is sort of a precursor to flying edges, also performs fairly well compared to marching cubes. But you can see that even in sequential mode, the flying edges approach is 5 to 8 times faster than the marching cubes algorithm. Now, if I use 36 threads and I look at parallel speedups, and I compare flying edges, synchronized templates, and an optimized marching cubes, you can see the performance numbers are on the order of, on this hardware and this operating system, about 11 times faster for the biggest data, which is 2048 cubed. So pretty significant performance increases. And that's, to me, when I write a threaded algorithm, if I can't do 10x or greater, on a, say, 8 core machine, I'm not happy. So there are a lot of opportunities for speed up. There are still a lot of algorithms out there that are sequential. And I think in some ways it's a golden age of parallel computing, because for so long we've been doing everything in a sequential manner. And a lot of people haven't really thought real hard about how to speed it up with parallel computing. So that's my part. I am going to stop sharing and let Spiros take over.
Okay.
And if there's any quick questions while Spiros is firing things up, I'm around. All right.
So let's
Thanks,
start.
Spiros.
Okay, I'll put that over here. Hopefully it won't affect me anyway. So yeah, we're gonna start with some extra parallel primitives, which is the thread local storage. So basically, the thread local storage is a mechanism by which each thread in a specific multi-threaded process has storage only for that thread, and this data that they are generated should only be accessed by one thread to avoid data races. So one thread can have, for example, an array, and the other thread should not access that array. The thread local basically thread local data can be used to calculate thread local results and then sum them into a reduction step. And since we're going to talk about atomics later, you should most of the times consider using first thread local approaches rather than atomic approaches. So as a side note to thread local, we should also take into account that, for example, when we try to sum an array of doubles, right? With many threads, the result of it is not going to be the same at every iteration, because the order really matters when you're adding doubles. So one way to go around it is to have explicit subranges or do a mapping of the input to the output. Now let's go to atomics. Atomics are basically a hardware implementation that allows us to do mutex-like things, but which are accelerated by the hardware rather than the system calls. For example, using a mutex. And the atomics can perform operations like load, store, compare, and swap, which often referred as cache, add, and subtract. And we use them instead of mutexes so that we can avoid data races. Atomics can also be used to basically replace mutexes as they are with basically implement spin locks, which are basically the same thing as mutex, but they're using atomics under the hood. And those spin locks can yield better results if used appropriately, where appropriately means that you should consider using atomics to implement a spin lock if you know that the chance of this of the acquiring of the lock is really high. If you don't think that's the case, use a mutex. Or we can go for optimistic locks. Optimistic locks are basically, you can try to lock, for example, a vertex, and if you manage to lock it, you are going to continue with your work. If you don't, you're going to skip that, and you're going to address it at some time point in the future using a load balancer. Those optimistic approaches tend to be, are for sure non-deterministic, but in some case, they are the only way, for example, in parallel generation. Now we're going to go into what are the memory orders in atomics. I know that's a bit of a black box for many people, so I'm going to try to explain them briefly. And if you want to look into more details, you can check out the link of the memory orders in the CVP reference. So the memory order relaxed is the cheapest order you can request to perform any atomic operation. The only thing that is guaranteed is the atomicity of the operation. For example, if we want to add numbers, if we want to add integers, we can do that using the relaxed. We can do counting. But if we want to have some kind of ordering per se, the relaxed is not sufficient. So another combo is the memory order acquire and a memory order release. We can use those two together when we want to lock something and unlock later. This way we guarantee that the order of both acquiring and releasing is correct. And another combo is memory order release and memory order consume. And you use that approach when you have a producer that says the memory order to release and a consumer that says the memory order to consume. Now, another tricky thing is the memory order acquire release and memory order sequential acquiring. And the difference between the two is that the acquire release can guarantee the ordering of one atomic variable. If you have more than one, you need to the sequential. You need to use the memory order sequential, and that's the case because basically under the hood, the hardware creates a stack of operations, and if you want to have two atomic variables that their order really depends, you need to abide by the order that they were basically executed. If you don't, you're going to have issues. If you have only one variable, acquire release is sufficient. The default in anything that you do with atomics is a sequential, is the last one, the red one, which is the most memory inefficient, let's say, memory that you can have. So always consider relaxed or acquire release, and acquire along with a order acquire and order release when you have a spin lock or optimistic lock, and release and consume when you have producers and consumers. I hope that I helped clear out some questions with that explanation. So now we're gonna go to some built-in parallel functions that are really common, the fill, which you can use to just, you have an array, you wanna fill with specific value, you can do it. And that's usually useful for initializing. You can also copy an array to another array. You can also transform an array to another array using a specific functor. And that can be useful, for example, when you have thread local results, and then you want to transform them to be global results. If you have, for example, if you have indices, you can transform them and you have the right bookkeeping indices to append all the thread local results properly. One extra thing is the sort, which it's really helpful because it's in place in the majority of the case, but you have the n log n complexity, which even with many threads, it can be a pain. and also you need to be aware of stable and unstable versions. Now, if you want to use sorting for operations like reduction by key, where we can see an example down here. So for example, we have A5, B8, A6, B4, and we want to basically create a list of lists. You can avoid using sorting, which would be the easy case to just sort them and just get the extents of every single key. You can avoid that by using counting, offsets, and a flat list of lists. And if you want to look into a specific implementation of how that would look like, you can look at in the VTK library static cell links. It's a common approach that actually implements that. Now, if the number of keys are different than the number of the unique keys. So for example, here, if we didn't have any duplicate, since we have duplicates, we need to be able to say which of the keys are actually going to be processed. So we can use the DQ to keep track of all the keys that are actually populated. And we prefer a DQ because you can append them in O1 when you do third local computations. So time for the case study of the surface extraction. So what we actually try to do here is, given a volumetric mesh, such as a tetrahedral mesh, hexahedral mesh, or hex dominant, whatever kind of mesh you have, we try to remove all the internal faces and preserve all the external faces. As you may imagine, the external faces are used only once, and the internal faces are used more than once. For example, as you can see here in the two cubes that are connected, we have two hexes. We would like to remove the interface quad so we can get the right-hand result. So only the surface of those two cubes. And that is really useful when we try to render an abstraction mesh without using any volume rendering. And it's also, it has been, at least for me in the past, particularly useful for debugging mesh generation algorithm, if anybody is working on that. So how do we actually do that? So first, that's the sequential version. First, we parse all the cells, and for each cell, we parse all the faces. We extract the IDs, the point IDs of the face. We rotate the IDs so that the smallest ID is the first. And then we try to insert that face with the IDs into a hash map. And the hash that we're going to use is going to be the first ID of the face. So we're going to, when we access that hash map with a first ID, we have a list. So each time we cannot find that that face into the list, we insert it. And when we find, we remove the existing face. So at the end, we're only going to have faces that existed only once. That's the idea of the hash map. That's why we use it here. And once we end up having a hash map with a empty list, a non-empty list, we parse the non-empty lists, and we parse the faces in those lists and uniquely insert those points in, of that face to get the output point IDs, and then we insert the face to the output. As you can imagine, there are many problems here. And the first thing, how do you modify the face hash map in a multi-threaded fashion? The second thing is, how do you allocate memory using the memory pool? Yeah, I forgot to mention that here, when we create the face, we allocate the face using a memory pool. A memory pool is a really nice contract when you want to avoid constant allocation. So you pre-allocate a lot of memory, and then you reuse it in the future. The other problem that we have is dynamic arrays, because they are needed to output points and faces. So we cannot do any kind of resizing because it's not that safe. And the memory allocation of dynamic arrays is slow when we try to insert points and faces. Also, point merging is not thread safe. And typically you use partial topological hash, as Will mentioned previously. So how are we going about dealing with each of those problems? So the first problem that we're going to deal with is how to fix the unsafe modification of face hash map and memory pool allocation. There are 4 options. The first option is to spin lock and modify the hash map and then when we try to do an allocation, we spin lock into the memory pool, and we allocate through that. As you can imagine, you have two spin locks for one on the point ID and one on the whole memory pool. Especially the second one is extremely difficult to handle. The second approach is to spin lock on just the point ID in the hash map and have thread local memory pools. The third approach is to have thread local memory pools and thread local phase hash maps. And once you compute everything that you need to compute, you have a reduction step in which you merge the thread local phase hash maps. And there's also a fourth option that I'm currently working on, which we perform a reduction of all the phases by their key, which is their hash value, the first point ID, to create a list of phases, and each phase is basically the cell ID and the phase ID of the cell ID for each hash value. And then we iterate over all the phases in each hash value using the DQ that I mentioned previously, and we modify the phase hash map at P0. The benefit of that is that you avoid any synchronization in the phase hash map, and you also use a thread local memory pool to allocate the phases inside your phase hash map. So the best one as of now, what I'm working on is the green, which actually we spin lock on the phase hash map on the P0. And the reason for that is that the chance of two phases having the same point ID, first point ID, is really small. Therefore, there's not going to be a lot of overheating waiting for one thread to finish and the other head to continue their work. As far as the second one, yes, it removes the synchronization, but you still need to pay in the beginning the creation of that list of phases, which is not cheap. So once we have basically our phase hash map with the list of phases, we parse sequentially and create a vector of phases. So that's basically our output phases. And then we distribute those phases to each thread so that we can later write into the output. We mark them in a point map. The point map basically is used so we can avoid having additional points in the output and only have what is actually used in the output. So we mark the original point that is used or not, and we also count the size of each thread's total phase to know where to write in the output cell array. Then we allocate the cell array only once. We don't need to do any kind of reallocation. We parse the point map sequentially to assign the output point IDs versus the original point IDs and calculate the total number of output points. And then we also allocate the output point array only once. And once we do that, we generate the output points arrays using the point map. We can also optionally output related data to the points. And then we generate the output cell arrays using the point map and the distributed phases across each thread. And optionally also generate the output data related to cells. So that's pretty much how the parallel version of it. Sadly, I didn't have the time to add to create results as far as parallel performance, but it got about 70% parallel efficiency, and we're going to discuss what exactly that is. So when you design a parallel algorithm and you write all the code and everything, then at the end you need to compute, okay, did you do a good job, yes or no? And the way to do that is to calculate the so-called speedup. The speedup is basically, in general, t time before your changes, t time after your changes. In our case, is time of sequential execution, time of parallel execution. So for example, if we have one execution that runs at 8 seconds, and in the parallel version of it runs in 1 second, and we have 8 cores, we're gonna have 8 as speed up. And the parallel efficiency of that is gonna be 8 by the number of cores so it's gonna be 100%, which that's like the excellent. That's the ideal. An acceptable parallel efficiency, it's above 70%. So if you don't have a good parallel efficiency, there are many things that could actually happen under the hood. The first and most important one is that threads either don't have the similar amount of work, or they don't have enough work at all. You should ensure that there is no empty work at every thread. You should also try to over decompose your results, because if you over decompose them and you distribute them, your load balancer is going to do the magic. Hopefully, for example, if you use the OpenMP, it has a dynamic load balancer, or TBB has also some other load balancers. The more you decompose your results, the more opportunity you're going to create for your load balancer to balance the difference between two threads working at the same time. Also, another thing that is really important is memory writes and reads. That could be one of the cases that your parallel efficiency is not right, because you're trying to access memory in a non-cache friendly way. And when I say cache friendly, I mean a continuous way. So you jump from one ID to the other ID and back and forth all the time. You don't wanna, you wanna try to optimize to not invalidate your cache more than the times that is needed. And also another reason that you might not have perfect parallel performance is if you're using some kind of mutex or atomics. You should try to minimize the use of it, or remove it completely if possible or worth it. When I say worth it, I mean perform actual analysis and see which one is the best. And some extra notes that you need to remember always: parallel is not always faster. It can be many times that it's going to be either the same or even slower. And we've seen that plenty of times in happening in VTK. So you should be really careful when to use parallel algorithms. And also, when you design a thread-safe parallel algorithm and everything is nice, you should also analyze the performance using both many and one thread. And I mentioned specifically one thread because with one thread, it's really easy to figure out what's the bottleneck in your code. You cannot, it's really hard to estimate the performance, the parallel performance. But thankfully, we have tools that can help us with that, such as Intel's Vitune, which I really, I use plenty of times, and helps me analyze both sequential and parallel performance. Of course, you're also going to get into the situation that something is not working, you have a race condition, and you need to figure out what's happening. So things to keep into account is ensure that the memory access is thread safe. That's the most important thing. If you don't, you're going to have sex faults all the time. Also ensure that functions that are used are thread safe. And last but not least, use thread sanitizer. The thread sanitizer is basically software that will tell you if you do any of the above. If you have not thread safe memory access, or you're using not thread safe system functions. And that's all from me. Me and Will are both open to questions.
Any questions?
Was there a question that came on the chat? Or we have questions from the in-person audience?
I see one question from JC to help identify which part of the specific pipeline to parallelize. Usually, personally, I use Vitune, and I first run it sequentially and then in parallel, which lets me know which parts are actually need to be my focus on improving the performance. And once I do that, then I can actually delve into that particular piece of code and see what I can do better.
I have a question, Spiros. So did you say thread sanitizer in your response there? Was that the tool?
Yes. Yes.
Okay. And from your slide, it looked like that would help you identify problems with non-thread safe functions and non-thread safe memory access.
Yes.
I was also wondering about other things that you might run into, like, for example, I mean, I understand you would do simple timing to figure out your speed up, but are there tools or techniques available for identifying cases such as multiple threads all clustering around one shared resource and too many of them being locked out, waiting things.
Yes, yes. For example, in VTune, you can see during the execution of the time which threads are actually doing some work and which threads are not doing anything. It's the called utilization of all the threads. If one thread is waiting, then for sure you're not going to get any performance out of it. Or for a common thing that happens is one thread finishes its job and then has nothing else to do, and then all the others continue. Just because the others continue, you're gonna get that not good parallel efficiency. That's also something really important, which means that you didn't distribute the data properly.
Okay.
What kind of approach? So if you do see that your code is running like the distribution is not very good, what kind of approach would you take to make to improve that? I guess, like, what's the strategy that you would go through?
So can I jump in here quickly?
Sure.
Yeah. So what I see a lot of developers do is they will, it sort of depends on your perspective, whether you're bottom up or top down. A lot of developers come in, they use these tools like VTune or whatever, and they see bottlenecks and they start optimizing at a very low level, right? And that gives you performance improvement, but often it's modest. Sometimes what you have to do is throw away the algorithm and just completely rethink it. In which case you can get massive improvements sometimes, but it's a lot of work. So I'm not sure I'm answering your questions, but it's very easy to have tunnel vision and focus on trying to accelerate, like, data accesses and minimizing floating point computations and all that. Get your 5 or 10%, which could be great in some applications, but sometimes you need to throw out the algorithm and just rethink it completely and look at your computational primitives and see if there's a better way to design an algorithm with more data independence. And if you can do that, typically you can get really good performance and efficiency and all those good things.
Is there so some algorithms may be semi-parallelizable. Is there a approach you would do differently? If, say, for instance, some pieces could be independently run, but they still, you can't split it up too much based on like the limitations of the task.
Well, there's classic algorithms like streamline generation. It's really hard to make that faster. I mean, if you have 1,000 streamlines, you can thread each streamline can be computed independently. Now you do have issues with data caching and all that sort of stuff, but you can get decent performance improvement. But if you just have a few streamlines that are quite long and large, it's really hard to speed those up. Then you have to look at your data accesses and go really low level. And also, if you have some sort of spatial locators to sort of figure out where your particles are as they move, your supporting structures often can be sped up quite a lot.
Right.
But yeah, there's some algorithms that, you can beat on them as much as you like, but the inherent sort of dependent nature of them makes them extremely hard to speed up. But having said that, sometimes with visualization, you can take shortcuts. So rather than trying to create one long streamline, you can do something like a line convolution integral, a lick, something like that, where you basically create little line segments that use some visual encoding that's really clever. And when a human looks at it, it looks like you have a continuous scalar field of a bunch of streamlines, when in actuality you don't, in which case you can compute things much faster. So sometimes, in the viz field, we can play tricks with the visual representations to parallelize and make things happen faster. I mean, that's the beauty of SIGGRAPH, right? That's what these guys do. They find ways to make particle physics, which is very complex, look natural, even though they're taking shortcuts one right after the other. But that's clever algorithm design, and I think it's wonderful to see when people do it right.
Yeah, I think those are good examples. So
Hey.
I have you have one?
Oh, you have one?
Yeah.
Okay, we've got a deadlock right here.
Go ahead, you go.
I guess I was just wondering quickly about the atomics, and you talked about the different types of atomics. And I was just wondering if was a comment on how important it is to design, like look at your producers and consumers, and is it a potential real bottleneck? Just if you use the wrong design, is it a potential to really cost you a lot of time if you don't think it well up front and you get further in your algorithm?
If you don't think the memory orders of the atomics, you mean?
Or what type what type you're going to use?
If your operation is heavily dependent on atomics, for example, it's just read write, nothing, no computation, no real computation, maybe yes. But most of the times your algorithm is going to be computationally intensive. You're not going to see that. But when you try to tweak a little bit more the algorithm, you're going to get some difference when you use the right memory order. For example, in that particular code for the surface extraction, when I was using something else instead of acquire release to create a spin lock, I had two times slower speed, because the sequential write is really expensive. The sequential acquiring is really expensive, and you need to be careful.
Okay.
But if your core computation is not dominated by the atomics, then probably you're not gonna see it.
Yeah. Okay. Yeah. Go ahead.
Yeah, I was wondering about, so you mentioned some tools in your talk, which seem specific to C++ thread design. Are there any other tools that you would recommend for maybe Python or other languages, or that would help access some of these parallelization concepts?
I'm not aware, but I think there are some open source profiles that, for example, Perf, that can be used, but I don't know to what extent they go into and what they can do. I just know Perf that are common open source Linux software.
Okay.
So Jess, you know, a lot of times you just do very simple things like Spiros was saying, you run sequential, you run with n threads, and then you use different backends. You use TBB, you use standard thread, you use OpenMP, and switching backends, switching from many threads to one. If you start seeing seg faults and things like that, you can often narrow it down to a region of your code where you go, oh, there's a data race there. And that actually is pretty effective. But once you get to a point where you're thrashing, you know, you need to go to thread sanitizer or something like that. That will tell you where the races are and other bad situations exist.
Okay.
Okay, I don't see any raised hands in the participants list, so. And hit our 1 hour, so. I guess.
Well, I mean, yeah, if there's no other questions, we can end. I want to thank Will and Spiros for their talks and times and questions. I think it was really interesting. So
Yes, thanks again.
Yeah, you're welcome. It was fun. Thank you.
Yeah, we'll see you next time. So we have
next time.
Yeah, we have another panel discussion scheduled for 2 weeks, which will be on web deployment or visualization.
Yeah. Great. Thanks, guys. Take care.
Thanks, everyone.
Thank you so much.
Bye.
Bye.
Thank you. Bye.